If you've learned about AC generators before, you've probably been shown a diagram like this. A rectangular loop, a magnetic field, some arrows, and somehow, electricity comes out. But if you're honest with yourself, there's usually a gap in the explanation. Why does simply rotating a wire in a magnetic field create a voltage? Where does the force on the electrons actually come from? And why does the current reverse direction at all? Most explanations jump straight to the finished machine, and then try to justify it after the fact. In this video, we're going to do the opposite. We are going to build an AC generator from nothing, using only first principles physics, one step at a time. And by the end, you won't just know how a generator works, you'll see why it has to look the way it does. So let's start with a goal, and nothing else. What we want is a device that produces a voltage around a circuit loop that reverses direction continuously. In other words, an alternating voltage source that drives an alternating current, like you see in this diagram. Graphically, if we were to plot the voltage against time, it might look something like this. So to begin with, let's ask ourselves a simple question. What kind of physics is even capable of producing an alternating voltage like this? There are only two fundamental ways nature gives us a voltage, or more generally, an electromotive force. The first is through static electric fields, which we create by separating charges. This is exactly what batteries do. The battery forms an electric field around the circuit, which pushes electrons around said circuit. This constant field gives us a direct current. The second way to generate EMF is a bit more subtle. We need a changing magnetic flux. This is captured by Faradays Law, which tells us that the EMF around a closed loop is equal to minus the rate of change of magnetic flux through that loop. An example of this working is the electrical transformer. This device consists of two wires wrapped around either side of an iron core. When we feed a changing EMF into one side, it generates a changing magnetic field in the core, which we can denote with this vector field. This changing field means there is a changing magnetic flux through the second coil, and as a result, we see a changing EMF in the second coil also. All in all, if we want an alternating EMF, we just need one thing, a magnetic flux that changes with time. Everything else follows from that. But let's clarify exactly what we mean by magnetic flux, because it's not the same quantity as the magnetic field. Magnetic flux is a measure of how much magnetic field passes through an area. Here we've shown two magnetic blocks, which automatically generate a magnetic vector field pointing from north to south. If we now draw a 2D plane in this field, the magnetic flux is how much field passes through this area. Specifically, it is the surface integral of the dot product between the magnetic field and each chunk of area dA. Looking at one chunk of our area, this area vector is just a vector normal to the surface. You'll be able to see it more clearly in a moment. When we are considering a flat surface like so, we can simplify this integral to the dot product between b and a, which is just b times a times cos theta, where theta is the angle between b and a. Right now the angle is 0, as the area vector aligns with the field. At this point, the flux through the area is at its maximum. However, if we rotate our area plane, theta becomes non-zero, and the magnetic flux decreases. So all in all, the magnetic flux depends on three factors: the strength of the magnetic field, the area the field passes through, and the angle between the field and the area's normal vector. To get an EMF, we want this quantity to change. So, we have three options to do this: change the magnetic field strength, change the area, or change the angle. Changing the magnetic field strength is possible, but it's very inconvenient practically. Similarly, changing the physical area of a surface, which we might imagine is a sheet of metal, is even worse. But changing the angle is incredibly easy. We just rotate our surface. So this is our strategy to vary the flux. Next, we need an object to rotate that can accommodate an EMF as well as a current. Some sort of electrical circuit that can experience the EMF generated by the changing magnetic flux. Firstly, we'll obviously need a conducting material that allows charges to move. But we'll also need a closed loop, so that charges can actually circulate and form a current. And specifically, we want a loop that encloses the rotating area we've created. Why is this? Well, Faraday's law can be expressed in a slightly different form to what we've used so far. Up to now, we've considered directionless quantities that are the magnetic flux and EMF, but in full vector form, the EMF is the closed-loop integral of the electric field. And this is crucial because the electric field, and only the electric field, is what determines how electrons move. Lectures 3 and 4 of my basic electricity course covers this if you're not familiar. This integral, specifically, is the integral of E around a closed path. The path is simply the shape of our wire loop. The surface bounded by that loop is the surface through which we calculate the magnetic flux. Now here's the key idea. If the magnetic flux through that surface is changing, Faraday's law tells us that an electric field must exist in space, and it must circulate around the boundary of that surface. In other words, the changing magnetic flux produces a looping, non-conservative electric field. Here I've plotted the field vector for one electron throughout a full rotation, but we can do it for all the electrons too. This electric field only exists when the flux is changing. So, if we want a continuous EMF, we must keep changing the flux, meaning we must keep rotating. This is the magic of AC electricity. When we rotate, every half turn, the magnetic flux changes sign, so the electric field reverses direction. If we measure the EMF through our wire over time, we'll observe an alternating, sinusoidal plot. Now there are a few other practical design considerations we should mention. First is how we connect our wire to the circuit, given it is constantly rotating. For this we use conducting slip rings, which stay fixed in position and connect to a circuit externally. The other consideration is how we actually rotate our generator. Conveniently, there are many processes in nature that can do this for us. We could use the natural flow of a river, wind turbines, or rising steam, for example. As long as we keep the turbine rotating steadily, it will generate electricity for us. And just like that, we've turned a magnetic field and a rotating wire into a constant supply of EMF, yielding this sinusoidal output. But hang on, where does this sine wave actually come from? And what determines its shape and size? For this, let's go back to the fundamentals. As we know, magnetic flux is the integral of B.dA. For a flat loop in a uniform field, this simplifies nicely to phi equals BA cos theta, where theta is the angle between the magnetic field and the loop's normal direction. Now suppose our loop rotates at a constant rate. If it completes f rotations per second, then it rotates through 2 pi radians in one period. That means the angle varies as theta equals omega times t, where omega is 2 pi times f. So the magnetic flux as a function of time is phi t equals BA cos omega t. The field strength is constant, the area is constant, it is only the orientation that changes. We can plot the flux as a function of time like so. Now let's apply Faraday's law. The EMF is the negative rate of change of the flux. So if we substitute our expression for phi t into this, we get the EMF to be B times A times omega times sine omega t. And just like that, we have an alternating EMF. This is the mathematical function behind our waveform. If we return to our rotation cycle, this makes complete sense. When the wire is perpendicular to the magnetic field, the flux is at its maximum. Meanwhile, the change in flux, and therefore the electric field and EMF, are at a minimum. Likewise, when the wire is parallel to the magnetic field, the flux is at its minimum, and the change in flux is at its maximum, so the field and EMF are at their maximum. When we rotate the wire again, the field does point in the same direction in space, but relative to the wire, which is rotated by 180 degrees, the electric field is now in the opposite direction, hence the negative sign. Let's now analyze it. The sinusoidal function depends only on omega, which is just the frequency that we rotate our wire. One full rotation results in one full EMF cycle. This equation also tells us something important. The size of the EMF increases if the magnetic field is stronger, the loop area is larger, or the rotations are faster. The last point is especially interesting. If you spin the generator faster, the voltage not only oscillates more rapidly, its amplitude increases as well. This is a key design principle for real generators. So let's now put the whole chain together. At the start of the video, we wanted an alternating EMF. To get that, we need a changing magnetic flux. The simplest way we could do that is to rotate a conducting loop in a magnetic field. That changing flux guarantees a circulating electric field, and that electric field produces an EMF. And if the loop is connected to a circuit, a current flows. So in the end, the AC generator is nothing mysterious. It's just a device that rotates a conducting loop in a magnetic field, so that the magnetic flux through the loop changes continuously, and Faraday's law does the rest. So now we have a way of creating an alternating voltage source. In the previous video, we determined why we want to use AC in the first place. But what is this current? The voltage is well defined, but as we know, the current depends on what else is in the circuit. In the next video, we'll be looking at simple circuits containing resistors and see how the current changes. In turn, we'll learn about RMS voltage and current. P.S. I'm currently updating my app to include worked problems and solutions for all the videos on my channel. I'm also going to make worked practice problem videos in the near future. Stay tuned and subscribe for more. Thanks for watching.